hang in there. Gateway Dam, it'd really be nice to get that passed before break. I don't have practice tonight. There's some freshman games, so if you want to do it after school, you can come here after school. If that's a time that works for you, just let me know. I know we got some coming at 4 o'clock. So somebody just passed number 5. So, you know, hang in there. All right, so we got quiz tomorrow on these topics here. So we'll talk about the questions you had on the limits here in a little bit, and we'll review some particle motion problems, and then give you some more time. I've got a sheet here with a few more limit problems on it, the particle motion problem. We got this other packet. I got the answers to it, so we left. Right, I told you to maybe leave about 3 of these to practice today too, so if you've done that, I'll have some to work on, okay? And that'll be tomorrow. We were just talking about final. You know, I guess I kind of mentioned this at the beginning of the year, but I haven't really talked about it, I think, since. And yeah, just a quiz tomorrow just on these things, no final. And that's kind of because of 3 terms, so to me it's kind of makes sense to do a midterm, you know, 1.5 terms in, you know, roughly, you know, so we'll do one here like about 4 weeks after we get back, probably late January, early February. It kind of works good to do it, you know, we've got derivatives. You know, we talked at the beginning of the year, there's 2 main topics, I suppose 3 if you throw in limits because everything's based on limits, but really 2 main topics, which is derivatives and then integrals. And so we're going to be wrapping up chapter 4, probably end of January, and get kind of done with the derivative part, and do a test on all that stuff, okay? All right, so again, this was stuff we had up here yesterday. So position, velocity, acceleration, which is all those things that involve the chart, could be antiderivative, could be antiderivative a little bit, simple ones. Derivative, for sure. The chart, all those connections. Speed, increasing, decreasing, has to do with if acceleration, velocity have same or opposite signs. Total distance travel, we talked about that. We look at a scenario like that today, here again. And then all the limit problems that involve infinity, including L'Hopital's rule. So I've got that up here, here now. So I kind of put this together. This is a little different than I had it written yesterday. This kind of summarizes what we have right now, I suppose. So if you have a limit as x approaches a number, or you have a limit as x approaches infinity, plus or minus infinity, really one of 3 things is going to happen, right? You're just going to get a number answer, maybe a plug-in, or maybe common sense, or whatever. You know, you're just going to be able to look at it. You're going to be able to get a number. You know, direct substitution, that kind of thing. More likely what's going to happen is, well, then I jump down to number 3. And then the other thing that could happen is you get a number over 0, right? When we used to just say does not exist. So you get 4 over 0, 6 over 0, something like that. And if you get that, you know that's a vertical. We should know. We get 6 over 0, 7 over 0. That's a vertical asymptote. And then so we got this infinity situation going on. Now we just got to check each side. So it does not exist. But anytime now we have does not exist, we have to tell why, right? We have to discuss the one-sided limits, whatever. So check the left, A approach, as you approach A from the left, right, that's where you plug in a 2.999 and 3.001, whatever. See if we're getting a really big positive, really big number, right? And then the other thing and the most common thing that's going to happen will be the middle, right? You're going to get the top and bottom are both getting really big, or the top and bottom are both 0. Or maybe a 0 times infinity, which we talked about yesterday. And if you have those situations, you can do L'Hopital's rule. Or you can do the stuff we used to do. You can factor, you can do the conjugate, you can do bow tie, whatever. But you still might have an answer. Now, it might end up being does not exist. The top might be getting really big compared to the bottom, and so this might just go to infinity. So you might have does not exist, infinity, okay? Or the bottom might be really big compared to the top, so it might be 0. Or it might be some other number, okay? It might be some other number that it comes out to be. But so a lot of them will be in the number 2 category. All right? All right, homework questions. Homework questions. specifically on limit problems. I really have nothing else to tell you about limit problems right now. Just what questions you have.
Go over like 32 to 36.
Okay? So on this situation, we have a graph, right? And so on 32, and hopefully we'll have a little work time here and we can look up in the answer. But on 32, it says as x approaches 1. So as x approaches 1, when you look at the graph, so that's, let's go to, you said 32, right?
Yeah. So
32, so x approaches 2. So as x approaches 2, on the bottom you're getting 0, right? And on the top is f of x. So you plug it in 2, you get f of 2. Well, f of 2 looks to me like it's about 1.5, right? Does that make sense? You look on the graph. So on 32, it looks to me like we're getting 1.5 over 0, right? So which one of these three, where are we at in this one? We're down to number 3, right? We're getting a number over 0. So right away we know does not exist. And so now what we have to do is we have to check x approaches 2 from the left, x approaches 2 from the right. So Chris, I'm glad you asked about this one because this is a little out of the ordinary because it's got this graph in it. Definitely could give you one like this, right? But it's the same idea. So we want to approach 2 from the left. Now the top is still going to be 1.5, right? And the bottom is still going, and then the bottom is, what are you going to get if you have a little less than 2? So 1.999, right? So now the problem was f of x over x squared minus 4, right? Correct? On 32. So if I put in a 1.999 here and I square it, that's like 3.999 minus 4, right? It's a really small negative, right? So we're getting a really small negative, okay? So what's a positive divided by a small negative? Negative infinity. Makes sense? And 2 from the right would be 2.001. So 2.001 squared would be a little more than 4 minus 4. That'd be a really small positive. So we'd be, again, we're still getting 1.5 on top because, okay? And then so we got a really small positive. And so that would be positive divided by positive. That would be positive infinity. So there would be how we do it. Make sense? Yep. So I'm assuming that we just go through the other one. So number 4 or 33, you plug in 4, you get about 3.5 on top, and 4 minus 4 is 0. So again, we're getting 3.5 over 0. So you do the same thing. Now the difference here on 33, when we check x approaches 4 from the left and x approaches 4 from the right, so this is 3.999, this is 4.001. Now what we have here is f of x over x minus 4 squared, okay? So now what's happening? Well, you put 3.999 in minus 4, that's a really little negative, right? But then you square it, so what's that? Really little positive, right? Still really little, 0.001 squared is still 0.0, it's really small. So no matter which side of 4 you go on, you're getting a really small number and then you square it. So you're always going to get, so you're going to basically get 3.5 over a small positive both times, right? So what you have here is infinity and infinity, and of course we want to say this limit does not exist because right away we got that, but they're both going to positive infinity. So that would be a case where we would have that scenario there. Make sense? Okay. So basically the same kind of situation. While we're doing it, let's just look at the last couple. So x approaches 1, f of 1 is 0, so the top is 0, put a 1 in, f of negative 2, that's 0. So now we're getting 0 over 0, okay? So we got f of x on top, we got f of negative 2x on the bottom, we did x approaches 1, we got 0 over 0, so ideas? L'Hopital's rule. L'Hopital's rule. So what do? Derivative of the top, what's that? What's the derivative of the top? F prime. What's the derivative of the bottom? Negative 2 times f prime of negative 2x. Kick out a negative 2. Now we're getting a little off track here. I mean, most of our problems are not going to be this. They're going to be more like those other ones that we focus on. But, I mean, right? I mean, this is There could be a few problems like this. I mean, you got to be able to think this way. So now there we go. Now what are we going to do? We're going to plug in a 1. So f prime of 1 would be on top, and negative 2 times f prime of negative 2 would be on the bottom. So f prime of 1 would be the slope at 1. Looks to me like it's about, I don't know, 1.5. Okay, I'm just estimating here. F prime of negative 2 is pretty steep. Looks to me like it's about negative 2 times negative 2 is 4. 1.5 times 4, that'd be 3/8. I don't know, whatever, something like that. Okay, what do they have in the back? See how good. 34. What is that? 4.2. I'm just so confident I did good on that. 0.3125. What's that? That's not 3/8, but it's close. Okay. All right. So that's what they have. All right. Does that kind of cover that a little bit? Okay. Any others in there? Any others in any of them? Was 36 one we were supposed to do? Why can't we do that one that they say we can't? It's not 0 over 0, right? You put a pi in, cosine of pi is negative 1. So you get negative 1 on top, right? You get negative 1 over 0, so you can't use L'Hopital for it. Okay, all right, anyway. Any others? 42? 42, 42. Sketch the graph of a function that has all of the following properties. Be sure to label axes and indicate units on each. Oh, okay, that's a good one too. All right, so let's do that. All right, so has domain negative 3 to 0. So let's go by 2s here. Negative 3 to 0. All right, or no, not 0. Infinity. Negative 3 to infinity. So we can't go left of negative 3. Okay. Has a range from negative infinity to 2. So we're not going to be able to go. We're not going to be able to go above 2. F of negative 1 is 0. So negative 1, 0. 0, 0, and 5, 0. Okay, so it's got to go through those points. As x approaches negative 3 from the right, the limit is negative infinity. Okay, so no wonder it can't go past there. We have a vertical asymptote. So as we approach negative 3 from the right, this graph's got to be going down towards negative infinity. Okay? Asymptote. As x approaches 2, the limit has to be negative 3. 1, 2, 3. Now, does that mean there's a point there? What's it mean? No. Horizontal asymptotes are when x approaches infinity. You're thinking of the next one down. I'm talking about Roman numeral 5. X approaches 2, the limit is negative 3. What's that mean?
It's almost touching negative 3.
The what?
It's almost touching negative 3.
Could it be a point, though? What does this mean?
It just depends on the cars.
I'm just going to say, tell me about the cars. That's where the cars are meeting, right? At 2, negative 3, the cars have to meet. But the diner could be burned down, right? But the cars have to meet at that point. Okay, the cars have to meet at that point. So I can put a hole there. I've just put a dot there right now. The cars have to meet there. Okay, and then as x, down to the last one, as x approaches infinity, so way out here to the right, this graph has to be approaching 2. So probably coming up like so. Now, could this have went up and then come back down?
No,
because of number 2, right? If it was just up to number 6, the last one, then yes, it could have went up and come back down. But number 2 said the range is from negative infinity to 2. So it can't go above 2 because of that. But yes, because of so there's a horizontal asymptote out here, like so. And we can draw it all the way across, doesn't matter. So this graph's got to be coming up like so. Now, so we got everything, right? So now, and the rest of it's up to you, right? The rest of it is up to you. You can do whatever you want here. So this might come up and come back down and then come up here and then come down. And it might even go way down here. I don't know. This wouldn't have had to be a minimum here, right? You just go through it. The cars have to meet there. And it might come down here, and then it's going to come up here, and then it's going to go like that or whatever. Okay? So just go through each one, see what's happening. And so I don't know, who knows? It might have just come here and then back down, and then it might have been a minimum here, and then it might have went up and down again. I don't know. Whatever. Okay? Be creative with the rest of that. But it's got to have those parts of it. Yeah.
And the -3 part, shouldn't it be going down instead of going up? Because like it says, it's approaching -90.
As x approaches 3 from the right, so as the car comes in from the right, this has to be going down to -infinity.
I think that's right.
That's what it's doing. Well, yeah, that's what the little plus. All right. Good. All right. What else? Okay. $60. Limit as x approaches 0. Read it to me. Tangent, what is it?
Tangent 3x.
All right. So first thing we do is we plug in a 0. Remember, you got no calculator here, so you got tangent of 0. What's tangent of 0? If you don't know what tangent of 0 is, make it sine over cosine. Sine of 0 is 0. Cosine of 0 is 1. 0 over 1 is 0. So tangent of 0 is 0. Ln, but you got to know that, right? I mean, we got to know that without a calculator. We got to know those values. Okay, put in a 0. Ln of 1 is 0. That's another value we got to know. Ln of 1 is 0. Ln of e is 1. We got to know those values, right? Here's the Ln graph right here. It goes through 1, right? Ln of 1 is 0. Okay, so this is 0 over 0. So we can do L'Hopital's rule. That's what I would suggest, because to be honest, there's nothing else to do, really. Okay, so this is secant squared, 3x with a 3 kicked out, and this is 1 over 1 plus x. Now we plug in a 0 again. So we plug in our 0, put a 0 here, we just get 1 on the bottom. That's nice. And we got to plug a 0 into this. Now, some of you might not know what secant squared is. It's 1 over cosine squared, right? So I would probably turn it into this. Okay, 1 over cosine squared. Now remember what cosine squared is. Cosine squared is really cosine of 3x all squared. Okay, like that. So let's put a 0 into there. So we'll put a 0 into there. We get 0. What's cosine of 0? 1. 1 squared is 1. 3 over 1. 3. So the top is 3. 3 over 1. 3. It's possible that the most difficulty there is actually plugging in those values and being able to figure that out as opposed to the calculus part of it. Okay, but there you go. Okay, so the answer to 60 is 3. Now again, this would be good practice now, and you might want to take a picture of the book, but 56 through 80, that whole kind of section, right? Any of those would be good practice for them all too. I've got some on the on this worksheet too. Although I don't know if I have an answer key for that one. See if I can find it. All right. What else? Anything else?
76.
76. Read it to me.
Limit as x approaching 0 plus sine x times ln of sine x.
Sine x times ln of sine x. Okay, so you put in a 0, sine of 0 is 0. Okay, you put in a 0 here, sine of 0 is 0. Ln is 0. You can't do ln of 0, right? But what you have to think of, remember, x is just approaching 0. Now, is it x is approaching 0 from somewhere? What do you say? From the
right.
Right. That's how you say that. There you go. From the right. So as x approaches 0 from the right, okay, sine is, if you look at the sine graph, right, as you approach 0 from the right, you're approaching 0 from the positive side, a positive value. So you're putting in small positives. If you look at the ln graph, if you look at small positive x's from the right, what's this doing? Negative infinity. So what you have is a negative infinity times a 0 situation. That's where we said we'd like to flip this over, right? We'd like to flip this over. Now, it depends which one you want to flip over. If you want to do L'Hopital's rule, which is what I would want to do here, then we've got to flip this over. So this would be a pretty hard one. I mean, so if we have 10 of these, 12 of these, or whatever on the test, some of them are going to be fairly straightforward. Some of them there might be a few that are a little more challenging. This would be the more challenging round. So what I would do, I don't remember doing this one lately. I would probably flip this over. What's the reciprocal of sine? Because if I flip this, it's just 1 over ln sine x, and that's probably not a lot of fun to do. The reciprocal of sine is cosecant. So what I could do is I could take this, and I could put it down here as cosecant. Okay? Now, what I've got is infinity over infinity. I know that because I just did the reciprocal of 0. We talked about that yesterday. The reciprocal of 0 is essentially infinity. Okay? So I know what I've done is I've turned this into infinity over infinity, which means I can now do L'Hopital's rule. So what's the derivative of ln sine x? 1 over sine x times cosine x. Right? Derivative of the inside. That's the top. Bottom, what's the derivative of cosecant? Negative cosecant, cotangent. Okay? Now I'm going to plug in a 0. Now if I was doing this, I would turn these into sines and cosines. So what's this bottom? This bottom is really 1 over sine, and it's cosine over sine. Oh God, this is going to get ugly. This is going to get ugly. Wait a minute, not really. Wait a minute. Cosine over sine on top. Wait, this isn't as bad as I thought. What do we got on the bottom? We got negative cosine over sine squared. What can I do with that? Invert, multiply. So take this and invert. Oh yeah, this is going to work out nice. Look at that. Invert, multiply. What do I got? Cosines cancel. One of the sines cancels. Beautiful. X approaches 0. Sine of 0 is 0. Okay, what was that, 76? Okay. And, you look in the back, they skip a few steps. They did what I did. They wrote an ln sine x, and down here they wrote 1 over sine, right here. And then they jumped immediately from that to negative sine. Right? So they didn't show anything. But just drew the top, drew the bottom, and then I did some simplifying. Okay. So, yeah, it could be on there. It'd be a tough one, for sure. Mostly tough because of the derivatives, right? Hopefully you understand this part, right? You put in a 0, right? Sine of 0, 0, gotta know that. Here, ln of 0. Why is ln of 0 undefined? Why can't you do ln of 0? Because you get close to 0, it's going to negative infinity, right? So that's you can't, it's a vertical asymptote, so that's how you know it's this situation, right? So you need to flip one of those, so you get a 0 over 0 or infinity over infinity. So that's a basic L'Hopital kind of scenario, okay? And then the derivatives get kind of tricky. But again, that's why it's important to know all those derivatives, right? Okay, another one. We're on a roll. Anything else? Well, if you think of something, let me know. All right, let's talk about some particle motion. Then we can give you some practice for review time, and you can work on your own here a little bit. All right, so maybe, I don't know, just in your notes. Well, did anybody come up with, the other thing I told you might want to do is look at this old motion packet worksheet and see if you had any questions or anything came up that was a difficulty. Did anybody find anything there that they wanted to ask about? On that 1 through 16 page. asking. Or if you don't, or if you do and you don't want to ask in front of everybody, let me know later on. Okay? All right, so I picked out some problems that we could maybe give a try here. Let's see. Well, let's look at this one. Okay, just a few that there's probably nothing for you to write down, but we can just talk about here real quick. Okay, these are some problems from old. These are just some problems I've went and rounded up from old AP tests. Okay, and that's the same place I went to look for questions for our quiz too, as well. All right, here's a table of values with velocities on it. So what's this mean right here? What do you think of when you look at this table and you see the -1 right here? It's velocity. It's going to the left, right? It's going to the left. Then what? Going to the right. Still going to the right and faster. Now, what happened between 1 and 2? Who knows? Maybe something happened between there, but we don't know. But it seems like going to the left, going to the right, still going to the right, stopped, right? Not just slowing down, it stopped, going to the left. Okay. Which of these, at time 0, the particle's at the origin, which of these could be the graph of the position from 0 to 4? So we think it's going left, we think it's going right, we think it's stopped, it's going left, at least that's what that's telling us. Any of these you could rule out. A, B, C, D, E. We could rule out B. Why? Doesn't start at the origin. We could rule out D. At time 0, the particle's at the origin. This is the position graph. So this has to be a graph of its position. Okay? Those two don't start at the origin. Okay? So eliminate those. Okay? What about D? What about A, C, and E? Anything we can eliminate? We can eliminate A. Why A? Because it's going to the right at the beginning. Now, again, remember, velocity is the slope of position. So that means at 0, don't we have to have a slope of -1? That's another way to think about it. Remember the chart, right? All these connections we've had. Well, clearly that is not a slope of -1 at 0. Does that look like it could be a slope of -1? Looks to me like that could be a slope of -1. What about here? Seems reasonable. Okay. All right. So I would say C and E are both pretty reasonable. Okay. So what else? Do we use that same idea about slope? Well, let's do this. What has to be happening right here? So what's the graph have to have? Like a flat spot, like a local max, local min, something like that. Now, what do we think it is? Local max or local min? Max, just going to the right. Then what you have is F prime basically here changing from positive to negative, don't you, right? See how those things come back to us here? So at 3, we better have a max. And, well, both of them do. Okay, so that didn't help us any. What about, let's go back to that slope idea. At 1, we better have a slope of 2, right? Because this is going to the right at 1. So at 1, does that look like a slope of 2? Reasonable. What about here? No way. No way. Right? So it's going left, then it's going back to the right. Well, this one is a little too slow to get back to the right. This one is going left, and then right away at 1, it's going to the right, and it's going pretty good to the right. So it's got to be this one, going left just a little bit, and then coming back to the right. So C, right? So that would be, those would be your thoughts, position, velocity, acceleration. So it makes you think of that a little in different ways. Okay, let's go to this one. Okay, let's talk about this one a little bit. And you can write some of this down in your notes or not. Just follow along with me, whatever's going to help you here. Particle moves on the x-axis, so the acceleration is 15 root t. The position of the particle is 10 when t equals 0, and the position of the particle is 20 when t equals 1. What's the velocity of the particle at time 0? Now this one's probably got a little bit. I want to talk about this one, but it probably parts of this I might make you do, probably not both of these things here. But how do we get from acceleration to velocity? antiderivative. So what we have is, we have the acceleration. So we got position, velocity, acceleration. They started this way down here at acceleration. So we're going to need antiderivative. So we raise this up to 3/2 and divide by 3/2, which would be multiply by 2/3, which would be 10. So this going to be 10t to the 3/2 plus c. So here's the problem. What's the velocity at time 0? We don't know what c is, right? We don't know what c is. Now this is where it probably goes. We haven't done, this would be the first one of these we've ever done, so that's why I wouldn't put this on the quiz. But, so that's a velocity. Well, but they told us these two things about position. So what do I need to do? I need to go antiderivative again and get the position. Okay, so my position function would be raise that up to 5/2 and divide by 5/2, which would be the same as times by 2/5. And so that's what, 4? But here's the part we haven't done before. So, and then what's the antiderivative of c? What's the antiderivative of a constant? What's the antiderivative of 7? 7t, right? So what's the antiderivative of c? C times t. But then what do we got to do since we just did the antiderivative? C. Now that's a different c, so I better call those C1 and C2. Now, so again, we haven't done that. We will do that. We will definitely do problems like that. And that's why they gave us 2 things. So basically what we have is like a 2 equations, 2 unknowns kind of thing. Now, it's pretty easy actually, because here they tell us t is 0. Well, that's pretty easy. When t is 0, this would be 0, this would be 0, and so what's this c have to be? This c has to be 10. So it's not like it's hard. I mean, it's not like it's an impossible thing. It's just we got enough other things that I'm quizzing you on, so we won't worry too much about that. So we know that one's 10, and then they give us this one. When t is 1, it's 20. Well, that's pretty nice because 1's an easy thing to plug in. 1, that just becomes 1. So this is 4 plus c1 times 1. That would just be c1 plus 10, and that's got to equal 20, right? Well, okay, so that's 10. Take away 4, what is that, 6? So c1's got to be 6. So this is 6t. So there is our position. So our velocity, that would have been this c right here then, right? This c right here is the 6. Because we do this derivative, that'd be 10t to the 3/2 plus 6. So that's a 6 right there. Okay, so now, so we had to do that little extra bit of stuff right there to get that. Okay, but now we got our velocity equation. So when at time 0, when t's a 0, that of course wipes out. So our velocity is 6. And there we go. And there's an answer. Now, of course, remember when we talk about the EP test, not true on our quiz now, when we think about the midterm a little bit, it's about 2 minutes per question on these multiple choice questions as far as how much time you have, right? Because you got like 30 questions in an hour of no calculator ones. So, that probably took us a little longer than 2 minutes, but, when you're on a roll and you've been doing these, maybe it doesn't. But anyway, so there's one, just kind of along the lines of what we're doing. That was from 2016. This one's from 2014. Okay, let's look at this one. This one's a little more like what I might give you tomorrow. Okay, very much like that. Particle moves on the x-axis. Position is given by x equals this equation. For what value of t is the particle at rest? Okay, so here's your position function. What are we going to do? The derivative would give us the velocity, and then we're going to do what? Set it equal to 0. At rest means we want the velocity to equal 0. So the velocity, which would also be known as x prime of t, right? Either one of those you can write, doesn't matter. So what's the derivative of this? That'd be cosine 2 pi t times a 2 pi. Why do I do this to myself? Okay, times a 2 pi kicked out, right? Plus derivative of 2 pi t, 2 pi, right? We're doing the derivative with respect to t, and we're going to set that equal to 0. So we're going to subtract 2 pi. I'm going to put that around in front. So we got cosine 2 pi t equals negative 2 pi. I'm going to divide by 2 pi. So we got cosine 2 pi t equals -1. Would that be right? Okay, so then we ask, don't worry about the 2 pi t in there right now. When does cosine equal -1? Is that a pi? Now, the thing we got to think about here is we got t is between 0 and 1. Okay, but now we're not t yet. The inside here has to be pi. Now it could be -pi, but that's not going to work because we don't want t is not going to be negative. And it could go around again, that'd be 3 pi. That's probably not going to work. But so the inside 2 pi t has got to be pi. That's the one we kind of think is happening, right? So cosine is -1 when at pi. So 2 pi t equals pi. So then we divide by 2 pi. What happens? The pi's cancel. So we get 1/2. T equals 1/2, which is between 0 and 1. That's the one we want. It's a t equals 1. Okay? So there's going to be some polynomial ones. We'll get to that here in a minute. We'll look at that. But also some trig. There's going to be some trig stuff too. Right? So you got to know, you got to be able to handle that. Okay? So when is a particle at rest? T equals 1/2. Now what if they said, when's a particle moving to the right? What would we have done? We'd have done all of that, right? And then we'd have thrown in the number line. Then we'd have said, okay, it's stopping at 1/2. Let's check on each side. So we'd have come back to our derivative, which was up here, right? And we would plug that in. So you put in a 0. Cosine of 0 is 1. 2 pi plus 2 pi is a positive. Put in a 1. Cosine of 2 pi, what's cosine of 2 pi? 1. 2 pi plus 2 pi is, so it's moving to the right the whole time, isn't it? Okay, it's moving to the right the whole time. It's not, it looks to me here like it just stopped. That'd be like a flat spot. Goes to the right, stops, goes to the right. Okay? All right. But that's what we would have looked at. Okay? Is the particle, well, no, we'll save that for another question. We'll save that for another question. All right, let's get another one. This is from 2013. Okay? 2013. Particle moves on the x-axis. There's its velocity. The particle is at position x equals -2 at time 0. What's the position of the particle at time t equals 3? So we have position, velocity, acceleration. So here's the velocity. So what are we going to do to get position? Antiderivative, right? Look at me starting way over on the right again. Why am I so intent on running out of it? Okay, what's the antiderivative of 3t squared? Raise that up to a 3 divided by 3, which would be t cubed, minus antiderivative of 4, 4t, plus some constant c. But then they tell us this right here. When t is 0, the position is -2. So 0 cubed minus 4 times 0 plus c. Well, that's easy, 0. So c is -2. Right? C is -2. So position function is t cubed minus 4t minus 2. And so when t is 3, 27 minus 12 minus 2, 15 minus 2 is 13. Okay? All right, let's throw a few more questions in here. Kind of a messy one, but that's okay. When does this particle stop? When is this particle at rest? What would you do? 3t squared minus 4, set it equal to 0, right? So 3t squared would equal 4, t squared would equal 4/3, t would equal plus or minus, let's assume t is positive like they told us, so that would be square root of 4/3, which would be square root of 4, so it would be something like that, okay? Square root of 4/3. Now that's 4/3 is bigger than 1, so square root of 4/3 would be a little bigger than 1, right? 1.1 something, 1.2, right? 4/3 is 1.333. Do the square root of that, it's going to be about 1 point something, 1.1, 1.2, whatever. Okay, just so we got just a little bit of an idea where it is, but we would put, and I don't need you to simplify that or anything. You could have just left that square root of 4/3. I'm fine with that. Whatever. Okay, that would have been fine. But we would do a number, so that's where it's at rest. So that would be the answer to that question. Now, when's it moving to the right? When's it moving to the left? That kind of stuff. Or let's do this. The question I wanted to ask is it speeding? When is it speeding up? Right? When is it speeding up? I want to get this question in here. So when we say it's speeding up, what do you have to check? Velocity and acceleration both, right? So velocity, acceleration both. Now, number line. Now, if I just said, is it speeding up at 1, that's a little easier. Is it speeding up at t equals 1? That's a little easier. Then all I have to do is plug in a 1 into both the velocity and the acceleration, right? But if the question is just when is it speeding up, then you kind of need your number line. So here would be my square root of 4/3, if you will. So a 1 would be less than that. A 2 would be more than that. We come over here to our derivative right here. So we put in a 1, that'd be 3 minus 4, that's negative. Put in a 2, that would be positive. Okay, and then we need our acceleration, right? What's our acceleration? 6t, right? That'd be the derivative of that. Well, geez, t is always positive, so what can you tell about acceleration? Acceleration's always positive, right? So the acceleration's always positive. So after this, it's going to be speeding up, right? Because this will velocity be positive and acceleration's always positive. Before this, it's slowing down, okay? Does that make sense? It stops here, right? So it slows down until here, it stops, and then it speeds up, okay? So that kind of makes sense, all right? But if the question was, is it speeding up at t equals 1, then you would just do a of 1, which would be 6, and you would do v of 1, and that would be, what's v of 1? Negative 1. And you would say what? The particle is slowing down. So if the question was, is it speeding up at 1, we would say it is not. It is slowing down. And then I would say explain, and you would say because the acceleration and velocity have opposite signs. So this particle is slowing down. Okay? And that's what we were saying here. It's slowing down until here, and then it's speeding up out. Okay? So those are some of the things that we can talk about. We wanted to do a total distance traveled, but that one's kind of messy, so let's not do it on that one. Okay, that was 2013. All right, so let's go back to here. And I think we had one. I think I had one here. Here we go. Gosh darn it, I wish you could have given us these ones where we have to do the antiderivative all the time. That's acceleration also. Okay, this one isn't bad. Okay, so again, they give it to us they give it as velocity, and then you got to realize these are on the AP test, so they know you've already done all the stuff with antiderivatives and stuff like that, so we end up getting a lot of them where you have to do derivative and antiderivative both in the same problem, even though our focus is mostly derivative here. So I wouldn't anticipate you having to do a lot of antiderivative on the quiz tomorrow. It'll be more derivative stuff. Probably start you with the position function more, but could be the velocity. One antiderivative like this, to me, is definitely within reason for us to be able to do, especially this one. I mean, right? What's the, so let's do a total distance travel. Total distance traveled from 0 to 3. So what do we need? Obviously, we need the position function. We need to know where it was when. Start, end. That's all we need for displacement. Right? And we subtract those. What do we need for total distance travel? We need to know where it stopped, right? So it started, went to here, then it stopped, then it went to here, then it stopped, then it went to here, then it stopped, then it ended. Right? We need to know all those so we can subtract them and see where it was. So we need our position function. So what's the antiderivative of that? T cubed minus antiderivative of that? T squared. Antiderivative of that? T plus c. Position is 5 when t is 2. So t cubed So we get 5 when we have 2 cubed minus 2 squared minus 2 plus c. So 8 minus 4 is 4, minus 2 is 2. So 5 is equal to 2 plus c, so c is equal to 3. Okay, so c is equal to 3. So my position function is 3. But again, let's assume I just given you that to start with, right? So here's our position function. Find the total distance traveled. Okay, we just did part A actually, right? The position of the particle of A times t. So we did that. Total distance traveled. So we need x of 0. So where was it at 0? 3. Where was it at the end? 27 minus 9 is 18, minus 3 is 15, plus 3, it was at 18. So its displacement is 15, okay? But stopping points. So we need the velocity, set that equal to 0, okay? No calculator, so chances are pretty good it's going to factor nicely, and certainly looks like it does. So this would be t equals negative 1/3, which we can ignore, and then t equals 1, right? So it's going to stop, so the velocity is going to equal 0. This is our velocity. It's going to equal 0 at 1. So do we need a number line? I guess we don't really need a number line, do we? Not for just total distance traveled. A lot of times we would do a number line now. That tells you when it goes to the left, when it goes to the right. But we don't really need that unless it asks for it. Okay? So what we need to know is where was it when it stopped. So we put in a 1. 1 minus 1 is 0. Minus 1 is negative 1. Plus 3 is 2. So obviously this thing went left then right. Okay? We can even see what the number line is going to be because it started at 3, went to 2, then went to 18. So what's the total distance traveled? 17. So it went from, and again, make yourself a little x-axis here. So it started here, went to here, and then all the way out here to 18. So we'll have 1 here, and then 16 back to there, for a total distance traveled of 17. And then if I gave you some units there, like meters or something, then put the units on. Okay. Good stuff. So that's a little bit of everything on I mean, there's so much stuff that you can do with position, velocity, acceleration. All the chart stuff's on there, right? But the speeding up, slowing down, we did the displacement, total distance traveled. We got a little bit with derivatives, a little bit with anti-derivatives there. Maybe a little trig might get thrown in, whatever. All right, so this worksheet, I got some answers worked out for you. I think we had left 4, 6, and 7 undone if you want to do those, okay? You got some more limit problems in the book you can do if you want to take a picture of the solutions manual for practice. Here's some more limit ones. I tried to give you a little mixture. There is a, oh shoot. All right. I'm doing this problem up here, and I'm thinking, man, this looks familiar. That problem right there. Gosh, yeah, this factors nicely because I remember factoring it. Okay, but there's one part we didn't do. Is the particle speeding up at 2? So you can do that. Okay. Oh well. All right, so I'll see if I can find an answer key for this, or else I'll just work it out real quick for the top part of this worksheet.